Next speaker is Nils Reimers, got a PhD from the University of Darmstadt, sorry. He also did a postdoc there, and currently he's at Huggingface. You might know him as the creator of Sentence-BERT, which is a pretty popular learning framework for learning sentence representations. Okay. So please.
Okay, great. Yeah, welcome everyone. In my talk today, I want to talk about how to extend neural retrieval to new domains and new languages. So we heard a lot in the previous two talks how great neural retrieval is. And I want to put a question mark after that. It's like, neural retrieval really that great? So first, you have to train it on like really large data sets. So MS Marco has like 500,000 annotated data sets. But I mean, who has like 500K samples, training samples? You can be from a big company like Microsoft, that's easy. Or you run Google search, then it's also easy to get like 500,000 pairs of user interactions. But what about like new companies like Zeta Alpha? I mean, did you have, when you started it, 500K training data? Probably not. Academics, so your TUV, how do you want to get like this big data set? But also in big companies when you work on niche use cases. So you have some internal knowledge database where like, I don't know, 20 sales representation people from your sales departments are working. How do you get like such big data set for your internal niche product? And so for most domains, tasks, and especially languages, so if you go away from English, it's really, really, really hard to get any large training set. So all the retrieval work is only on English because we only have retrieval data for English, but go to any other language, even when it's high resource language like Spanish, it's really hard to get any good data sets for that. And so in my research, I'm really interested in how do models generalize to new domains and tasks. So can I just take the Test-B model from Sebastian and apply it to my use case? And how to improve the performance from unlabeled data. So my PhD student, Nandan Thakur, he created the SBERT benchmarking AR dataset. So far, dense retrieval in the previous talks were really similar in the setup. So we have some short question or query, and then we want to find some document answering this. And that works really nice. However, information retrieval is a lot more. So for example, here we collected 18 different data sets. One data set is, for example, you had a news article and you want to find tweets talking about this news article. Another one is to find counter arguments. So you have the argument coming to Amsterdam is great, and now you want to find counter arguments. So you should not come to Amsterdam. And so information retrieval is a lot more just than, okay, I have a query, I have a question, and I want to find a relevant paragraph. And here we compiled 18 different data sets in 9 different tasks. And we took a lot of systems and benchmarked them. And what we found is that BM25 is actually not that bad as proposed before. So here in the benchmark, we see on how many tasks are the systems better than BM25 and how often are they worse than 25. So Task-B, it's really nice on 8 tasks, but on other tasks, like, okay, you have a complete news article and now you want to find tweets about this new articles. Sadly, not that performing well. Even such, Task-B was by far the best dense model which was available at that time. And what works really well is BM25 plus cross-encoder re-ranking. So that worked really nice for a lot of different data sets and tasks. And also Doc-T5 query was also a really nice system that generalized well. So you have to be careful what you want. Do you want to have like do you have some specific use case, like at Zeta Alpha, you have research papers, you have a query or some question and you want to find information? Or do you want to cover the whole spectrum of information retrieval, even going into abstruse things like news article and finding tweets, relevant tweets for this news article? However, information retrieval benchmarking is extremely difficult. So for every benchmark data set, only a tiny fraction of query document pairs are annotated. And you assume, okay, all the other pairs are not relevant. An issue is that how do you get these annotations? Often you take some existing systems. In a lot of cases, you use some lexical systems. And then you show these results to user, to annotators, and they annotate, okay, which are relevant, what is not relevant. And we were asking like how many unannotated documents are systems retrieving. So this is also known as whole at K. So for example, for BM25 on track COVID dataset, 6% of the results was never seen by an annotator, and we do not know is it relevant or not. However, when you go to a task B, like 1/3 of the documents it was retrieving for track COVID, no annotator has ever seen it and was assumed to be irrelevant. ANSI, a different model from Microsoft, the dense retrieval model, had also like close to 15%. And what we did is like to annotate these holes. And what you see is that the performance changes. So for BM25 was a small hole rate. The performance difference is just small. So here we had like all the hits annotated and we found all the relevant passages. However, for example, ANSI, the performance increase is quite big. So also before we concluded, okay, ANSI is a really bad model for track COVID. After that, we say, no, it's really good. So in summary, be really careful with these benchmarks, how they were annotated, and do not see them as static and try to chase a leaderboard. Say, okay, now we are the best on whatever track COVID, but also update your data sets as you update your models. So as we already heard in the previous talk, we know that there are like different types of models. So they are like the re-ranker models, and then there are the bi-encoder models. And we know that the cross-encoder model, they achieve better performances. They also need less data. So if you go down, if you see here, how the performance drops for the cross-encoder and for the bi-encoder, we see that the cross-encoder generalizes a lot better with less data. And also it's also more stable to new domains. However, sadly, the cross-encoder is a lot more compute intensive. So also Nandan Thakur, he proposed Augmented Expert, where it's similar to what Sebastian said with the teacher, where we first trained the cross-encoder, and then instead of just staying on the same data set as MS Marco, we took a large unlabeled data set. So, I mean, you're not restricted to just 500,000 queries from MS Marco, but you can potentially take a lot of data, and it's also quite easy to get like new data. For example, for Zeta Alpha, you don't maybe know what people are searching and what's relevant, but you know what people are searching. So what's the query they type into, and getting this data is quite easy. So you annotate them with the cross-encoder. This gives you the silver data set. You train your bi-encoder, and you can see quite nice improvement of up to 6 points when you stay in domain, or up to nearly 40 points when it's cross domain. So when you just have some training data in a different domain. So finally, we also looked into, my student Keishing Wang looked into how to do domain adaptation. So we have some dense retrieval model, for example, trained on MS Marco, and now you want to use it on a different domain, for example, medical publications, and it does not perform that well. What would be nice is to take, for example, the nice TASB model and adapt it to your medical publications. However, so far we were not successful doing that. Only the other way around was successful. So we take an unlabeled data set. So you take all the medical publications you have, you do some pre-training, there you can use math language modeling, or what also works nice is a denoising autoencoder. So you take your text, you randomly delete words, you encode it to a fixed embedding, and then you do the decoder where you try to reconstruct the original text. And after that, you train on MS Marco, your model. And what we see, so we tested it for on sentence embeddings and also for semantic search. And we see quite nice improvement for math language modeling and also for the denoising autoencoder. However, the improvement is not like, okay, you get like 20 points better, but the improvement is so far only like, okay, between 2 and 5 points better on these data sets. So math language modeling is also still a really good system. We tested a lot of different systems, CT, SimCC, BERT condenser, and so on. And they were often, the performance was often not so good, or even a lot worse than math language modeling. So also be careful when you read about read about papers which claim, okay, we're amazing, but they just evaluated on one data set. Often the picture is a bit different when you evaluate it on multiple data sets, and then sadly it does not work that well. Okay, finally, as mentioned, we have a lot of good data sets for English. So for English, it's really easy to get the data. But for other languages, Spanish, Netherlands, German, it's really hard, and even worse when you go to some low resource languages. So how to make embeddings multilingual was, I think, is still a really interesting question. Best scenario is you have authentic training data. So if you want to have a Japanese model, you have actually Japanese search queries, for example, and Japanese text answering these queries. However, as mentioned, it's often really hard to get them due to copyright, due to not availability of these, due to, okay, it's a low resource language in general. So two alternatives is, one is you translate your English training data set. So this works surprisingly good. The other is to use multilingual knowledge distillation. Multilingual knowledge distillation works in the following. So you have some teacher model, some dense teacher models. So for example, you take the Sentence-BERT model, you input parallel data. So you have some English, Japanese text, you input your English text into the Sentence-BERT model, and you get some embedding for the English text. And then you take a student model where you input the English text and the Japanese text. You get two vectors, one for English, one for Japanese, and then you do a margin, a mean squared error loss. So you want to have the English text be as close to the Sentence-BERT point for the English text, and also the Japanese text should be as close to the English point of the same text. And this works surprisingly well. So this also works quite well into when you have just small parallel data. So for example, when you just have dictionaries or when you use wiki titles, you can get quite a good improvement using such a distillation approach. And another nice thing is this is not limited to only like 2 languages, but you can have parallel data from machine translation community for 50 languages, for 100 languages, and then make your models available for a lot of different languages. And you can use all the good quality, for example, from the Sentence-BERT model and transfer it to your multilingual model. You can also use like the clip model for images and text and make like a multilingual clip model to embed text and images in a lot of languages in vector spaces. However, this has quite some limitations. So if you translate the English train data to a different language, the issue is that other countries have other search interests. So for example, if you look into MS Marco, there are a lot of queries how to do taxes in the US, and it's about like special questions. Okay, how do I get tax refunds? If I assume, maybe we can ask the people from Google here what people in the Netherlands are searching. I would assume that they are not so much interested in the US tax system and how to get refunds, but they search stuff which is specific to the Netherlands, terms specific to the Dutch tax system. And so, and you do not capture this when you translate your English data. So you do not capture any specific things about the Netherlands or about Japan. So, and the same issue you have with multilingual knowledge distillation. The other questions like, do you have like good parallel data from your specific domain? If you have like a platform to search research papers from AI and you have parallel data from, I don't know, from movies, there are hardly any questions, scientific questions in different languages in these movies. So still the biggest limitation is good data, and please, if someone could collect good data, multilingual data, would be so much help for the community. Okay, so summary, first part summary. Neural search has issues to generalize. More data helps, and also compute intensive models are better. So we saw that the cross-encoder and Colbert are better than dense retrieval models, but they are a lot more computationally expensive. Knowledge distillation across architectures is powerful. So you can take knowledge from a cross-encoder, or you can take knowledge from Colbert and then transfer this to a more efficient student. Domain adaptations so far can give some improvements. So when you do masked language modeling or TSDE pre-training on your specific data set on scientific papers, for example, it can give you some improvement, but not like, okay, it's not like the powerful thing which solves every issue you have. So it's not like, yeah, not the holy grail of neural search. Multilingual models, you can get to a certain degree with machine translation to translate your training data or to use multilingual knowledge distillation. However, authentic training data is missing. And another issue is also we do not have any evaluation data sets. So we do not even know how big is the issue and the gap in this area. To finalize, so I advocate a lot, okay, how to go into like low resource, not needing training data. And now the questions like training procedure or training data, what's more important? So who thinks data is more important? Raise your hand. Who thinks, okay, model is more important? Raise your hand. Okay, still few. Yeah, so in academia, we like to work on models. And also previously, we heard how people work on models and it's exciting. If you're not in academia and you want to build a product, my recommendation is to work on the data so that the data is way more important than the training data, than the training procedure. So for example, we have here the really nice TestB model, and we have the performance on MS Marco, and we have out of domain performance on some obscure data sets, scientific publications, for example, from Track COVID. And we get really nice improvement by this sophisticated training procedure. However, so in July, we had like a sprint or community event at Huggingface where we grouped together to learn JAX. And there we collected also a large data set for embeddings. And we, instead of like 500K pairs, we collected 200 million pairs from Stack Exchange, from Wiki Answers, from Cura. We took a really simple training method. It was in total like 5 evenings. And we got like really nice improvement, not only in domain on MS Marco, but also out of domain. Because yeah, a model trained on 200 million data points is a lot better than a model trained on only 500,000 data points, independent how good the training procedure is. And now I think what's really interesting is like, okay, take the 200 million, compare it with TestB and see what you get out of this. So if someone has some compute power, it would be really nice to fill in the missing spot. Okay, so some teaser. So here at Huggingface, we're working also on Project Infinity, so we know in neural search what helps is the larger model. So a larger model generalizes better than a smaller model, and also the cross-encoder generalizes better than a bi-encoder. But these are really compute intensive. And the team at Infinity, they are working on a containerized solution. So you can deploy it to your own cloud. You say, I want to use this Huggingface model, and you get inference times, which is a lot faster than the original Huggingface transformer. And we were able to bring down the inference time on GPU to 1 millisecond and then CPU to 4 milliseconds for neural search applications. So yeah, instead of working on smarter models, just take a larger model and get the really good results. Okay, so to really finalize my talk, the biggest challenges in search, I think, is how to update models. So BERT has no idea about COVID-19, about BERT, about Zeta Alpha. And BERT also thinks that Obama is still the current US president. So how can I infuse new knowledge into pre-trained models? Low resource learning, how can I reduce the need for training data? And also, how can I make models generalize well? So far, we know large and slow models generalize well. Smaller and more efficient architectures have issues to generalize to different domains, different tasks. And how can we make a good, efficient model that also generalizes well? Thank you very much.
All right, we're gonna open up the question. Wow, I see a lot of hands raised. So let's start here.
Hi, thank you. Amazing talk, very comprehensive. I wonder about multilingual data, but when one sentence comes from multiple languages. So for example, if you look at Dutch social media, you will see those amazing tweets, for example, written in 3 languages at the same time. Is this something that you have encountered when building those models? And if not, what's your intuition about that?
Yeah, code switching is quite common. So it depends a bit on your background, on your culture, or the country you're from. But for a lot of countries, code switching, where you switch between, I don't know, Dutch and English, is quite common. Here, I mean, it's depends again on the training data. So if you only have English training data, it does not work. If you translate it just to Dutch, it might also not work well. That's why I meant was, okay, you need authentic training data, like how do people in the Netherlands write on Twitter, write search queries in Google, what is like responses they find relevant or not. And then if you have this really authentic training data, then you will also find these code switching. And models should not have an issue to learn these. We have like really nice multilingual models, which have like no issues to do the code switching.
Hence,
I have a big fear of missing out on JAX. Do you think, should I drop everything? Should I just drop PyTorch and TensorFlow and start JAX right now?
Yeah, maybe we can have panel discussion on that. I still prefer working in PyTorch, not in JAX. I found it a lot easier to do, a lot more convenient to do. Debugging is nicer, but people at Google will probably disagree with me on that. So maybe we can have like later here, like a stage, and someone who's like JAX into AWS could argue with me what is better, PyTorch or JAX. But if you work on TPUs and on Google Cloud, JAX is good thing. If you have GPUs, I prefer PyTorch, but personal opinion.
good to know. All right.
Hi, thank you. I very much enjoyed your argument for better data. And so I would like to ask you, in the very beginning, Jakub said something about that transformer models are state of the art on all benchmarks now. And I was already a bit frowning on that because, yeah, we have seen tasks where actually BM25, when well optimized, is still better. Yeah, in this light, can you comment a bit on that? So why does Jakub think that that is the case? Or is it correct in some context? Or what is your opinion on that?
Yeah. So what we tested here is like zero shot. So the model were not trained on like this obscure, I have a news article and I want to find tweets discussing this news article. And here we see that these models do not generalize that well in many cases. BM25 is like really nice and strong. It just looks like 4 common words. Also, BM25 builds up a knowledge about your corpus because it computes the inverse document frequency and knows which words are common, which words are not. And here we applied some models from MS Marco, from Bing Search, and now they should work with tweets and news articles, and they really fail. If you have training data and a sufficient amount of data, then it's able to beat BM25, I would say, in most or all cases.
All right, so we're gonna do a couple of last questions. I see more hands than spots. Gonna go. Sorry. Maybe we can extend it. Now we're gonna have a coffee break, so maybe you can just all chat.
Thank you. Thank you for the very nice talk. You mentioned in the end something about transformers, very efficient transformers in the Infinity library, and them running on CPU in under 4 milliseconds or about 4 milliseconds. I wondered, could you elaborate a bit perhaps on exactly what you did to the models? Are these the same models? Are these the same number of parameters? What exactly did you do to bring down the efficiency?
Yeah, so I'm sadly not the lead on the project. So my colleagues Morgan and Jeff, they asked me to present it here. So there are like different techniques they used as like model pruning, model quantization, and also to optimize the complete execution pipeline. for the specific hardware. So they were collaborating with different hardware partners from NVIDIA and Intel and see, okay, how can we do the fastest, I don't know, dot product multiplication on an Intel CPU or on a NVIDIA GPU to improve the inference time. But yeah, for more details, contact Morgan.
Thank you so much for the talk. I was wondering about the multilinguality embedding distillation, because like same sentence with same meaning, two sentences in two different languages, they have different order of tokens and probably number of tokens are different as well. Is it easy in this case to compute those MAC losses?
Yeah, I mean, at the end, it doesn't matter if it's like different order, longer or shorter. You just pass it through the student model and it gives you like a fixed number for the embedding, for the text embedding. So, and then here you have like just 768 dimensions, and you can just compute the margin MSE loss, not the margin, the mean squared error loss. And so it doesn't matter which type of languages you combine, how long are the sentences, as long as they represent the same meaning, you want to have them close in the vector space.
All right.
All right, so now we're gonna quickly go to the coffee break, but before that, I would like to close off with one question myself that I didn't get to ask yet. So I noticed a bit of a a negative feeling on where the space of domain transfer is right now in retrieval. You mentioned that it's good, but it's not not great yet. So my question is, in general terms, how hopeful are you that you're gonna bridge this gap in the near future?
It's hard to make predictions about the future. So I think, I don't know, it doesn't matter if I'm hopeful or not, but I think it's the only way how to really scale the models. I mean, when we look at BERT, it's just from 2018, it's not really old, but missed a lot of things which happens in the world, like COVID-19, work from home, stuff like that, has absolutely no idea about that. And how do we update the knowledge in these models? Of course, we could always pay new annotators. That's hard. I think the only way is really to learn from the text itself, so that you have some constant stream of text from Wikipedia. You see all the edits on Wikipedia, all the things people post on Reddit, on Twitter, and somehow learn it in the models. It's easy to do it in a pre-training step, but how do you do it with fine-tuned models? So you have some model on NER, named entity recognition, how to update this model so that it knows what is BERT and Roberta and XLNet and GPT-3. Yeah. Maybe question mark.
Maybe Daniel later will have some answers with the knowledge graphs. I don't know if everyone will agree with that, but looking forward to that.